Hello, what I would be eventually delivering from now is an entire lecture series that revolve around the topic real-life applications of soft computing. So as you can see, one of the key elements of this entire lecture series would be the applications domain. And how do we solve these applications? By the very paradigm of the solving tool known as soft computing. But if you look at the physical world right now, there's so much that computation has given to the society. There's so much that we see was eventually not automated and is now into the automated world. Robots have completely changed the entire scenario in which we weigh and think. Now anywhere you go, you are assisted by a robot. Now, whenever you call, you might not even be having a person who answers your call. It might be an automated systems altogether. Systems can see you going about and they can kind of optimize themselves, they can kind of provide you solutions with them. Now naturally, into a society where the manpower is going at a very high rate, the kind of payments are increasing at a very alarming rate, you need automated systems that are able to partially and later on completely replace humans in all these tasks that were else considered clergy in nature. You need systems to do tasks that would be impossible for the human beings to do. Into the past decade, we've seen immense application where automation has changed the society. So one thing that we're going to do is we're going to highlight all these applications that come up from various domains. There might be applications from the wireless remote placement. There might be applications that we take from the biometrics. There would be applications from the biomedical domain. We take all these applications and what are we going to do with these applications? We are going to solve them using the various fundamentals of soft computing. So before we even touch anything from the application domain, let us be assured that we are all aware of the numerous possibilities, the numerous applications, the numerous work areas that exist. So even before we move on, it would be important to realize what soft computing is. What are the tools and techniques in this computing technique that have kind of changed the entire paradigm of computing, that has brought in a new dimensions into the thinking of the people who used to solve these real life problems. So eventually in this lecture series, what we are going to do is, first we'll touch upon some soft computing techniques. Once we touch these techniques, the other thing that we're going to do is we'll pick up some application areas. Into all these application areas, we'll try to highlight how the things that we studied in the soft computing techniques can eventually be applied into the application areas, and how can we make real world systems deployed into the industries, deployed at various places that we see around, deployed into your homes. How do these work? Once we get into these application areas, the other thing that we would like to do right towards the end is to understand the limitations, understand the guidelines, and try to take motivation from these application areas. Is how is it that we can try to modify our systems, make them more scalable, in trying to identify what the problem lies, in trying to make systems that are much better than the previous systems. And that is what opens an entire paradigm of thought into these application areas using these techniques. So the kind of thought they multiply, they open all new dimensions, and that is what takes us into deep research that millions of researchers, millions of girls, millions of people, millions of faculty are doing all around the globe. So to start off, at this very first hour, we'll just try to touch upon some of the basic principles of soft computing, and we'll try to give this entire paradigm a very primitive, a very basic a very genuine shape into how all these things happen, into all that it will take for us to build some really, really interesting problems, some really, really interesting systems, which we are either seeing now or we would be seeing somewhere into the near future. Series happens to be the word computing. Now, computing is something that we all have been trained right from our very initial courses. So computing is something that we all learn either in form of programming techniques or in form of computing that happens into the image processing domain or computing that happens into the databases. They are all nothing but forms of computing where you take in some inputs, you try to play around with them, you try to see all that is out around your system, you try to do some sort of calculations, you build some algorithms based on those inputs, based on any state of the system as well, or maybe sometimes randomly in nature, you do some kind of calculations, you do some kind of algorithms, and then you get in some kind of output. For long we have been used to some very, what is now known as hard computing type of jobs, where we were given definite inputs, we used to do these calculations, we used to apply these algorithms and produce a class of highly definite outputs. So probably if you were asked to say what is 2 plus 2, you could say 4 without doubt. It was always asserted. There was nothing involved in this 2. There was no impreciseness involved, there was no assumptions involved, you could perfectly figure out the outputs. This is what now we call it as the hard computing. The very basic paradigm where everything is precisely known, where everything happens as it has been planned, where everything happens with complete preciseness, with of course the basic assumptions that your entire system altogether or your entire algorithm altogether may have. But the problems that we see in real life, they can never be solved like this. Try to make an algorithm that tries to match whether two faces match with each other or not. If I give you a string ABC and I give you another string ABD, you can perfectly find out whether this string matches with this string, which in this case is no. But I give you two faces of people, you probably might not find this problem the same as this problem. No algorithm would be able to perfectly determine whether this face belongs to the same person as this face. Of course, you would be able to determine whether these are precisely the same faces by pixel matching, but you can never be sure whether this face is exactly the same as this face. So problems are really complex in nature. The real world problems are really, really complex in nature. They cannot be solved by precise algorithms. So what we do is that we insert some kind of softness into them, and the field that evolves is what we're going to study is called as soft computing. So we're taking the same example where we had two faces and we had to determine whether both the faces belong to the same person or not. By the way, this is one of the problems that we would be taking in further lectures that belong to this lecture series where we will be dealing with the complete paradigm of biometrics. But to start off with, there can be a difference in the way these two images were taken. One can be from a very short vision, one can be from a long vision. There can be a problem in their orientation. One face was a pixel left and the other was a pixel right. There can be some noise here. There can be some expressions over here and so many things. So a perfect algorithm you will not be able to build. Into this paradigm of soft computing, what we will be dealing with is the addition of some softness can give us really good systems that is actually able to identify faces. Now remember, identification of faces is something that is eventually there at all these social networking sites, or even if it's not there, it would be soon coming up at the other websites. So it's the addition of some softness is able to solve a real good problem. So we would never mind the softness coming up into nature. Of course, a system may not give you the perfect answer. It might identify a face wrong. It's not never guaranteed that a soft computing system will give you a perfect answer because of the softness that has already been induced into the system and is now a part of your system. But we would look in this entire course in how the softness can say the two faces match or not. So even when I say that I'm introducing some softness, I might not be able to say that the two faces match or the two faces do not match. I can always say that these two faces match up to the degree of, let's say, 99.9%. And 99.9% is by the way high enough for me to make a commercial system out of it. If you give some 1,000 images, then one image fails, which is like the person whose image fails may consider some other means in which he enters the system the other way and his face gets identified correctly. So the basic fundamental of this technique is how the addition of some softness can make a problem that was erstwhile insolvable into a solvable problem. Now if we look at through the near history, soft computing is there at every place. Not only the experts of soft computing try to make in soft computing systems that are there everywhere, but it's also the other systems who try to enter into this field and solve their particular problem of study by using these soft computing systems. Now even before we start this lecture series on soft computing and its application into real life problems, it would be important to note, if you can anytime come up with a perfect algorithm that can solve the problem precisely, soft computing is not the solution for you. If you can anytime come up with a problem whose solution is known precisely, whose solution can be computed using any set of trivial algorithms, any set of new algorithms, and that is able to give you a precise answer within the time constraints, within the data constraints and all the types of constraints that exist in the system, so computing would not be the technique for you to apply. We apply soft computing at only those systems that are unable to provide a precise output. And then we, of course, by applying some impreciseness, we see into it whether it will be made any use to us. So we've done with something known as computing. We've almost done with something known as softness. Before we continue, another term that is very much prevalent into any kind of discussion when it comes to modern society is known as artificial intelligence. Of course, by its very theory, by its very definition, what this term means is that any way by which I can induce some kind of intelligence into a system that it's not natural to it. Or by some means, if I can introduce some kind of intelligence into machines, because machines are eventually something that I would try to make them intelligent. The humans and the animals are already intelligent. I would not try to use some artificial means into them for their intelligence. If I can get some kind of intelligence into them, into the machines, I call this term as the artificial intelligence. Now the entire discussion into the business community, into the soft computing community, into any community belonging to the sociologists, the geologists or anything, you probably don't discuss the term soft computing with them, you discuss the term artificial intelligence as them. It's like a kind of a bigger playground where people are trying to extract more out of systems, they are trying to extract more out of machines, they are definitely trying to extract more out of anything that might be in them, what eventually was only possible for the humans to extract. That's the term of artificial intelligence, and again, that very closely means machine intelligence, because I've said it's ultimately the machines that are trying to make intelligent. Another very close term is known as computational intelligence, because of course when I'm doing things artificially, I'm trying to use some kind of computation technique. I'm ultimately trying to use some kind of calculations and trying to introduce intelligence into the machines. One paradigm that has never changed is that any kind of system that you have, any kind of computer system that you have, any workstation that you have will ultimately operate on bits. It will always work on zeros and ones. It will almost always use only addition, subtraction, multiplication, division, some logical operators, and all those operations, all those trivial operations for their system. So what we are trying to do is that we are trying to use these basic fundamentals and we are trying to make them intelligent using some computation techniques, using some high-end algorithms. The very term artificial intelligence is again made possible. In fact, the early research into artificial intelligence started with something that is known as logic. Logic is again something that is very much prevalent into our day-to-day conversation. Logic is something that is an extremely overused term, because we solve problem and when we are able to solve them, we say that it was logic. It was some simple common sense. It was a simple work of some numbers, and we got it because we had some kind of logic with us. So we try to use the word logic, and we would be trying to see in how the word logic can be used in a practical system, and how can we make this word applicable to a system. How do we induce a logic inside a machine? A very basic fundamental would be I say if a state in which a machine is, it satisfies some condition, then I take a decomputed action. So again, a very fundamental thing that we almost in some or the other sense, in its most trivial format, we do it by the if or the branching statements at any of the programming language. I say if my system is at a particular state, it satisfies some particular conditions, then I take on some action. Now eventually, if I make this a very abstract term and make the action a very abstract term, I just use the word that if the vegetables in house are less than some computed number, then you just buy vegetables. And the system gets some kind of intelligence that is already induced in it. Because next time you will not have to go and buy the vegetables, the system will take action on its own. It will know when is it exactly that it needs to take an action, when it is that the action needs to be provoked. A set of complex states, a set of complex conditions, a set of very complex actions that can ultimately change the state, and all these fundamental systems, when backed up by some kind of knowledge representation technique, turns out to be known as what we know as the production systems that are entirely driven by some kinds of rules in nature, that are entirely driven by some kind of logic in which we can use a set of pre-computed rules, in which we can use a set of pre-computed logic that can act over a system, that can find out what the condition of the system is, that can fire the actions. The actions may again change the system state, that may again make the system to move from one state to the other, and eventually new rules being firing at a system of time, at a system of space, or whenever interrupted by the user or by any additional machine or by any additional system or by its own system. It makes it a complex system that we know by the paradigm of production system. Now all it takes to start up the very paradigm of inducing intelligence into a machine, that you might do it at any time, at any level of learning, is by making in simple systems that are able to act in this manner. It is by making simple rules that are able to do something. And then of course, into the later stages of the course, we'll look at it to what are the advantages of it, what precisely happen to be the disadvantages of it, what are the limitations that we would like to improve, what are the limitations that we probably cannot improve, what are the limitations we can improve by this having some other constraints that might hold true, that might not hold true, and all these wonderful types of systems that we would be doing out here. But the basic paradigm of artificial intelligence is to induce intelligence artificially into the system. Now, in this entire discussion, we haven't kind of delved into the word intelligence, which is seen by 10 different dictionaries with probably give you 10 different definitions. It's a highly abstractly defined term. As no two humans can say what is intelligence and what is not intelligence, what we would use the word intelligence is anything, any system, any mechanism that is able to solve a problem that otherwise would have required human intervention, that is able to have some kind of attributes into the system that is able to be, that can be used for problem solving. So we're there through with the basic principles of the artificial intelligence. We already know that the motivation is always to use some kind of technique by which we would be able to apply some kind of softness into the system. With this we move ahead with the paradigm of soft computing. Now again, before we deal with the individual techniques that are there into this problem solving methodology, before we even deal with any of these individual techniques, we'll try to give in a very broad picture at this introductory arc, and of course in the later sessions and so, we'll see into how the individual techniques work. We'll try to delve directly into them. We'll try to see how the individual systems behave in multiple scenarios, and how they can be adapted to multiple scenarios, and what is there inside the system. We'll have an inside out look into at the later stages, but here it's important to understand what the big picture is. So when it comes to the paradigm of soft computing, we have something known as the artificial neural networks, we've got something known as the evolutionary computation, we've got something that is known as fuzzy systems, we've got something known as heuristics. Of course, there isn't any big preciseness or impreciseness issue in heuristics. Sometimes it might be dealt outside the issue of soft computing. It will normally not be included into soft computing when it comes to dealing with literature. All these three systems introduce some kind of softness in nature. And of course, we can use multiple computing techniques in the same system. So it can be one technique assisting the other technique, it can be into the master slave mode where one technique follows the other technique, it can be two techniques supporting the other technique, it can be any kind of system that is made using these three fundamental pillars of the neural network of the evolutionary computation, the fuzzy inference system, and of course, along with that, the underlying principles of heuristics. So a very broad outlook into what these systems are all about. And of course, all of these are used to solve problems, all of these are used for solving all the various kinds of problems, like from robotics to biomedical to biometrics, these systems are used. Neural network is a basic inspiration from the human brain. Here we try to introduce some kind of characteristics into a system. We try to architect the system in such a way that it behaves similar to the brain. Now the brain has various parallel processing agents that's called as neurons. In fact, they are the biological neurons. They work all in parallel. They do some kind of computation, and whatever we sense, either in form of the sensory organs that we have, they kind of compute something, and that is responsible for our actions. So of course, by this it is clear that there is some kind of input that is to the system, and there is some kind of output that is associated to the system. The neural network, when I say they are problem solving agent, I mean that if you given some input to a system which already has something known as a state, it will provide you some kind of output. In fact, that is the very basic fundamental when it comes to any computationally intelligent technique. That's a very basic term when it comes to algorithms. That whenever given an input, you are supposed to provide an output based on whatever is your state of the system. The state in a pure algorithm sense, in the language of pure basic algorithms, it would be nothing but a set of predefined global values. It would be nothing but a set of predefined variable values that ultimately affect the computation from the input to the output. And whenever you apply the input, you always get in some output based on the system state. Now when I say that the system is actually a neural network, I get an exciting thing. I get a very exciting thing that the algorithm, in place of being written by a human, is written by the neural networks. So if I have got a set of input patterns, I may or may not have a set of output patterns. I have this entire collection of inputs and outputs. What the neural network does is that it tries to write an algorithm, it tries to make a system architecture, it tries to make a system that on its own knows how these inputs convert to these outputs. That is what is the exciting thing behind the neural networks. They are automatically able to find out the patterns into the inputs, and based on those patterns into the inputs, they are able to find out what the output would be. And that is what makes these systems really, really intelligent in autonomous sense. That is what makes these systems really intelligent. Now what would be the use of neural networks is that you know that you got an algorithm that links the inputs to the outputs. So whenever the system be given any kind of new input, I know what to do with this. Now if seen as a very big picture, I just had myself a set of inputs and output patterns, but what I have done with these neural networks is a complete system that is able to give answers that, of course, with the other assumption, with some softness induced, gives them correct outputs. The other paradigm that I would be taking in this series is, of course, the fuzzy inference systems. These are again systems that produce some output based on some inputs, and of course they also have a state that characterizes the system. They again follow these things, but how the fuzzy inference systems work is on a set of predefined rules. Rules that are given by the designer, rules that you should know, rules that the person making the fuzzy inference systems tries to formulate as approximately how these inputs are related to these outputs, and the rules are nothing but a set of if-else clauses. So if some condition is true, there will be an action. If it's not true, there can be any second condition in which there can be an action, and so on. Of course, exactly the same thing we were doing when we discussed about the paradigm of production systems. More or less the same thing that we were trying to do out there. The very good thing about the fuzzy systems is, again, they are known for their impreciseness in nature. The very good thing about the system being fuzzy is that there is some kind of impreciseness, and how this impreciseness in modeling of the input, in modeling of the output, or in modeling of the system state, that is in form of these rules, in how these impreciseness can lead to really, really good systems that are much applicable to real-life solutions, that is much applicable when it comes to the paradigm of fuzzy systems, is what we would be taking up later in this world. Now again, fuzzy is itself a very, very kind of primitive word. This entire paradigm of fuzzy inference system, when under exhaustive research, in exhaustive development, and under exhaustive kind of treatment from the community, what it has led to is a very good field of study that is known as the granular computing. these are the better picture of the entire paradigm of fuzzy systems as we've got. We will not deal up with much of the issues of granular computing, but what granular computing again does is that how introduction of impreciseness into working of the inputs with some set of rules can provide up with some outputs. Granular computing deals up with the various ways in which we can have this kind of impreciseness induced into the system. It deals with how the various kinds of impreciseness can be modeled to make up some real-world systems for the real-life applications. The other thing that we would be dealing is again a very much extensive, very broad field of study that is known as the evolutionary computation. Evolutionary computation, by its very mechanism, it means that it is inspired from evolution. It is inspired how we evolve from one generation to the other with our offspring being better, being able to perform tasks much better than we are able to, and their offspring being able to do it even much better. Of course, the system changes, the environment changes, these systems are able to incorporate these dynamic changes as well. So into the paradigm of evolutionary computation, we will be taking a very basic motivation from evolution, and we try to develop artificial systems on the lines of this evolutionary computation, modeled in a variety of mechanisms, modeled in a variety of ways, modeled in a variety of means, and we would be dealing in how we can make some real-world systems. Now, evolutionary computation is primarily used as an optimization tool. If you got a system, you would like to tune it up in some means. You try to do some fine tuning to it. The tuning can be very little, the tuning can be very much. This is done by the paradigm of evolutionary computation. And using this tool and how evolutionary computation can be used as an optimization tool, we'll solve some numerous kinds of problems that we all will have in real life scenarios. Evolutionary computation, of course, started out as mainly an optimization tool, but today we do not use it just for optimization. Evolutionary computation is used to design a complete system. It is used to architect the complete system. It is used to architect systems that ultimately develop systems, and all this exciting field of work that we receive by the evolutionary computation. So using neural networks, and of course the underlying assumption that they make, the underlying inspiration from neural network, the underlying advantages, using fuzzy system, using evolutionary computation, we'll have a look into how the soft computing works. Now whenever we deal with hybrid computing, that is addition of use of more or less any two of these systems, any three of these systems, all of these systems, or sometimes even any one of these techniques within itself. Any one of these techniques in multiple copies, we'll try to see how the world we move about with hybrid computing. The other word that would assist us when we deal with hybrid computing is the term known as heuristics. Heuristics is whenever we try to induce some kind of rules into the system, whenever we try to induce some kind of scores into the system that are able to judge these systems, that are able to guide these systems from one state to the other. We'll try to see in how forming some strategies, we'll try to see in how forming some scoring mechanism, we'll try to see as how forming some rules, we'll try to see as how to addition of some human intervention into the system can ultimately lead to a better kind of computation, and this is how heuristics tries to assist in all these fundamentals of soft computing. We'll try to see how heuristics assist each one of these problem solving methodologies. We'll try to see how we can make in some really good excellent system by using this entire picture of soft computing. Now we've used terminologies known as problems a lot during this entire course of lecture. We've used the word problems quite a lot. Before we solve any kind of real life applications, a motivation needs to be there that all these different applications ultimately converge to a standard set of problems. They almost converge to a standard set of requirements, and that is why soft computing is a module that can always be plugged into any of these software applications, and that is what makes the system complete. So for different applications, we need not have different techniques we'll be using. We'll be modeling the problem in such a way that the same module of the soft computing technique can be used at these problems. What we would be dealing up in this lecture series, the word problem, we'll have something known as a functional prediction problem. We'll have something known as a classification problem. And of course, one thing that we would be dealing with is an optimization problem. Again and again in this entire lecture series, be it the theoretical domain, be it the application domain, or be it the guidelines domain as I stated upon, we would be mainly revolving around these three fundamental pillars. We'll be basically revolving around these three fundamental problems. When it comes to any real life problem, you can ultimately model it up as either a function prediction problem, or classification problem, or an optimization problem. When it comes to function prediction, what we would be doing is that we try to make it predict a function that when given an input x, it produces an output. We'll see in how we can make this kind of systems that try to predict some kind of function. When given an input, they produce an output. Of course, the entire computation of this function need not be done by the technique. It can always be assisted by a human. It can always be assisted by any other agent. So, into a very broad sense, we will be trying to find out in how an input gets converted into an output. Whenever I deal with the word function prediction, I essentially mean that the function prediction problem is continuous in nature. So whenever I deal with the word function prediction, I would sometimes assume that the outputs are kind of continuous in nature. So I can have outputs of the point of 7.5, I can have it as 8.1, I can have it as 9.2, I can have it as 8.8, anything. And of course, these are into a continuous domain. At the binary, the decimal sense, I can always have as 87654 anyway. Function prediction problem, I would be assuming that the outputs are in some way either in integral form or in decimal format or in any other base. They are continuous in nature. The thing is exactly the same when it comes to the classification problem with one minor difference. The things are exactly the same when it comes to the classification problem with one minor difference. Here also the outputs are some function of predefined input, but the problem is that my output is a class. Now what the word class is, what do we mean by a class is a very basic fundamental, is that my class can be either A, it can be B, it can be C or anything up to let's say Ci. My output will be precisely one of these. I can never have anything between B and C. My output will always be a very hard output. That is one of this all possible set of classes. Any kind of output that I produce in a classification problem is one of this entire set of possible classes that the system knows. Of course, meantime we model the classification problem in a sense that the system refuses to give an output, so that's allowed. The system completely says that I cannot give the output, that is allowed. But whenever the output is given, it needs to be one of the various possible classes. So output is firstly discrete in nature. It is very much discrete in nature. And secondly, any of these classes, they do not lie at some range. I cannot say that B is closer to C and A is far away from C. I cannot say anything like that. They all represent independent classes and my system has to give an output as output one of them. Of course, many times that we solve problems, we say that classification problems are almost function prediction problem with the output being discretized to some of the classes. In some system it may work, in some system it may not work, as we would see out in later stages of the course where we touch upon some real life application. We would see in how these two problems differ and what exactly is the use of classification problem that we make it a completely different paradigm out of it. The other underlying fundamental is the word optimization. Now, optimization is that there is a system, I will have even wrote the word F for that sake, that behaves based on some input and output and some state. Optimization deals with it, I can tune in the system in which I can try to change in some parameters of the system and I can have an even better system. Now of course, AP system solves problem. If I given an input, it's soft computing, so it will give me soft output. Now any kind of output is valid. The motivation lies in making systems that are able to perform better. So if it's a face recognition system, I may say that my face recognition system is 78% correct. I do not say that my face recognition system is very precise. It might happen very rarely in nature. Now the basic fundamental of tuning is to make it a system that in place of 78% it will give me 88% and in place of 88 it might give me 98 or 99%. Correct. So that is what I will be doing by the various domain of optimization. Now as a problem, optimization always regards at some parameters. So let's say there was an x1, x2, x3 and up to xn. My inputs give me some outputs provided the set of parameters is something, it's constant. If I change in these parameters, my system for some input will give me some other output. Of course, this is what we do as by the word state. If you change the state, it will give you some different kind of outputs. We model the optimization problem only for this lecture series as this kind of problem, wherein we try to apply some kind of optimization over the system and we try to get the correct output. We try to get it as better outputs as possible. Of course, the other kind of definitions that we normally deal with optimization, where the optimization is supposed to reduce a system or to increase a system, are all valid. That is what ultimately we resort to. So that is the problem being fundamentally classified as a function prediction problem where the outputs are continuous, as a classification problem where the outputs are one of these possible classes, or an optimization problem where some kind of tuning in our case to the system is required. We'll try to use all these soft computing techniques into each one of these. We'll try to use these techniques and try to see how we solve this problem. So that is more or less towards the introduction, where we'll try to use all these techniques, and we'll see towards the later stage of the course, we'll see as how to these techniques get used to make some real life system. Another very important paradigm when we deal up with any kind of system that we'll see more or less more towards when we touch the application domain, not less right now, is the very term of noise, and sometimes it has to do a lot with the word uncertainties. You make a face recognition system, you do not know whether the face has been correctly captured or not. There can be some noise at the capturing level. You apply some kind of filters to do all the various kind of things, you don't know whether those filters were correct, they might introduce some more noise out of it. You might further process it, applying some kind of technique, some kind of computation over it, some kind of binarization over it. You might not come to know whether that binarization itself results in some more noise into it. So whenever we deal with soft computing systems, we can never assume that whatever is given the input is correct. it is always prone to some noise. Now uncertainties is a very different term. What if it happens that I use a sensor to record temperature, and the temperature is one of my inputs to the problem, and it does not record anything? It fails. Now I cannot say that there is noise, because noise is what 45 degrees centigrade by some technique would have been recorded as 46 or 44. That would have been noise. Here I don't have an input at all. That is what is known as the uncertainties. Whatever system we would be dealing, whatever computation we would be performing, whatever we would be doing out here, it will be with the assumption that there is a possibility of noise, there is a possibility of uncertainty. Of course, to different degrees when we talk about the different systems. And the last thing that I will touch upon right now, I talked about the input and the output, and of course the state. The state is specific to the system. It is specific to the technique being used. Whenever we deal with system design using soft computing technique, it would be firstly assumed I know exactly the number of inputs, the types of inputs. I know exactly the number of inputs, the types of outputs. I know exactly what my inputs are and my outputs are. So whatever problem we deal, if the inputs and outputs are not known, I'll try to model the problem in such a way that the inputs and outputs are known in any of the real life problem. I know the number of inputs. I know if there is an I1, I2 and IN. I know exactly what is this amount. I know exactly what is this amount. Computers, that is the tool of solving all these problems. They only understand bits which ultimately get converted to real numbers. So any of my input will be a number that lies between some lower bound and some upper bound. This would be again an assumption. The output again, it would be a number that lies between some lower bound and some upper bound, only because the computers are able to process it. So when I say using known inputs, known outputs, real number inputs, real number outputs, bounds and all these things, that brings me to exactly what this course is all about. There is an application and there is a tool. When I deal with application domain, I'll try to model up the system in such a way that this tool can be used. So I'll try to limit the inputs, outputs, the numbers and everything. While I'm dealing with tool, I'll try to model up the system in such a way that it can take precisely the same inputs and the same outputs as was modeled in this problem. This is what we would be dealing as the first unit when it comes up into the use of these tools. And this application along with this interface is what we will be dealing from the subsequent two units, where we will take in some specific applications of soft computing, and using this how we'll see as how the entire system can be formulated, as how the entire work can be done. So that will be all for the first lecture. Next we'll start off with the application of the expert system and the entire domain. That will be another work of the application domain.